Okay. Hello. Hello. Good afternoon. Hopefully my sound is on. All right. So what time is it? So it's 1 a.m. in Japan time. Let's get started. Okay, so hello, this is Junichiro Horikawa. This is the live stream tutorial live stream for Houdini, which is called as a Houdini algorithmic live. And today is 121st one, and the topic today that I'm gonna show you is a rainbow simulation. So I'm gonna show you how you can create a rainbow simulations using Houdini from scratch using pretty simple algorithm. Yeah. And I'm going to show the volume, I'm going to show the rainbow on top of the volume, like here, which is pretty easy to do. This is the one you actually see from the camera, and this is the one that's looking at this image from other view. So this is the way rainbow works is the relationship between the angle between the camera view and the sunlight. So you can only see the right one. The left one is kind of a analytical view which never be able to see from in the real world, but it's still interesting to see. I mean, it's in the virtual world you can see from any angle, so that's interesting. And using the same algorithm for the rainbow, you could use a point light as well instead of sunlight to simulate the rainbow, which would make some interesting effect like these. So I'll show you how you can do that as well. Okay, but first off, I think I should explain how exactly rainbow works, how exactly rainbow is being created or can be seen physically, so that we'll be able to implement it in virtual world. So I don't have a tablet today, so I'm going to switch it to a camera view to write some sketch. Hopefully you can see it. All right. So the algorithm for the rainbow is pretty simple. First of all, I think you can imagine when you can see the rainbow. It's most of the time it's after the rain, and that is because the rainbow will be seen on top of small water droplets like these. And by reflecting the sunlight with the droplet, you're actually seeing the color. Okay, and the angle difference between this reflection angle and the eye angle makes the color difference. And when the light reflects inside the water droplet, it actually reflects a little bit inside a water droplet like this. Based on the refraction rate, it's based on the wavelengths of the light. So based on different colors, it has different reflection rate, so the angle, the reflection angle differs based on the the light wavelengths, which makes a ray comes like these. Okay. And probably this angle, the steepest angle, could be a red, and the bottom angle would be a violet, and in between you have like something like yellow and so on. And you can based on the eye angle, which you are looking at the water droplet like this, or maybe somewhere else. Let's say you are looking at this direction, and by calculating the angle between this eye view, the view angle, and the reflection angle, in this case this theta, and by evaluating what theta is, you can actually say what color you can see. And it's the angle rate is in between something like 170 something to 129 to 178, something like that, and that is written on the paper, so we can look at it right now. Let's check. So if you search for a rainbow simulation algorithm or something like that, you'll be able to see a paper called Physically Based Stimulation of Rainbow. And this is a paper explaining how you can simulate the realistic rainbows in computer graphics. Though the method explained here is a bit complex because it's trying to simulate the physics property precisely, but I'm just gonna get the essential part so that we can make it really simple. So here it explains the reflection part. So based on the wavelengths, the reflection angle changes by reflecting the light inside a water droplet, and the angle difference between the red to violet is written here on page 4. So this theta 137.7 for the violet, 40 nanomillimeter wavelengths, and the red light is red light is this angle, and the violet angle is this angle. So the angle difference between the red and violet is just like 2 or 1.9 or something like that. So it's pretty small angle difference, and in between those angles you are seeing those rainbow colors. Okay, interesting. So what we need to do, what we need to just do is to estimate the angle between the view direction and the sun direction, and calculate the difference between the angle difference between 137.7 to 139.6, so that we can estimate that there's going to be a rainbow color in between those angles. and we can create the color value by using these wavelengths. The red, 700 nanometer, and the violet is 400 nanometers. Now there is no straightforward equations to convert from wavelengths to RGB colors, so we're gonna look for some equations online for that. Okay, but it's pretty simple. Let me just first search for that. Okay, so wavelengths to RGB, simple algorithm. Stack Overflow. Yeah, so this is one of the complex formula which explains how you can convert the wavelengths to RGB, and it also has a C source code, which is nice, but it's a bit overwhelming. It's a bit too long to implement in short time, so let's try another one like this one. This is more lazy algorithm, which still might work for quick prototyping, so I'm just gonna use these one for today. But if you want to have more precise color conversions, then you might want to try to use this one instead. But I guess this one is okay. Alright, so let's have this to convert from wavelengths to RGB, and using these information to convert the angle to a rainbow color or wavelengths. Let's just try implementing this from scratch. Now, I think it is better to implement this from a simple like setup. So I'm gonna start by simulating the rainbow on a grid first. Then later I'm gonna bring the same algorithm into volume. Okay, so that will be easy to understand. So I'm gonna create a geometry node. I'm gonna start by creating grid. Let's make this XY plane. I'm gonna try to show a rainbow color on top of this grid as a first test. So consider this is a flat layer of water droplet. Each point stands as a water point, or some kind of a mist wall of the mist or something like that. Okay, and what we wanna calculate is the sunlight direction to each point and the view direction from the camera to each point, and compare the angle between, calculate the angle between the eye direction and the sun direction, and based on the angle I'm gonna decide what color each point will be. Okay. So let's increase the number of rows and columns. Alright. Like 100 by 100 might be good enough for testing. Okay. So let's start by creating a directional light. I mean, it doesn't have to be a real light, but maybe it's easy to control. So let's have distant light as a directional light. Okay, and let's bring this and rotate this randomly for now. What we want to have is this directional information from this light. Okay, and we also need the camera, because we need the angle between the camera view and this sunlight view. So let's create camera. Okay, and let's bring the camera somewhere around here. Let's also split the view to two views so that we can use the left hand side as a analytical view or another perspective view so that we can control the camera view without interfering the rainbow. Okay, so let's have, I want to change this to perspective. Okay, so this, the right view is coming from the camera 1, which is used for rainbow simulations. The left one is just to check how it works. Okay, so we have a setup. Let's try simulating the rainbow using point wrangle. Okay, rainbow sim. Hello everybody. Thanks for coming. So first of all, we need two informations. One is the light, directional light information, and the camera information. So let's bring that. I'm gonna create a parameter for this node. Which is the operator path, so that we can select the directional light. And the camera. So that we can extract the directions and positions. Okay. All right, so let's first select directional light. It's inside OpG, distant light, and the camera is this one. Okay, so from the distant light or directional light, you just need the forward direction. So let's try to get that information first. Okay, so how we do that? We can use a VEX code called OpTransform, which will give you a transformation matrix from specific path. So the path that I'm looking at is this directional light, so CHS. Okay. Now this will give you a matrix for a light transform. I think. Let's check. Let me check the geometry spreadsheet. Yeah, so I'm getting those 4x4 matrix, which includes the position, rotation, and scale of this node here. Now from those informations, what I just need is the direction. So let's try to get that. And I haven't come up with an easy way to get the forward direction. Maybe there is one, but what I'm gonna do is to first get the rotational information or Euler informations from the matrix, then convert the Euler rotation to quaternion, then use the quaternion to rotate the negative z-axis so that it will become the forwarded direction of the light object. I'm just gonna explain how I can do that. So first I'm going to crack the transform, this one, so that I can get the rotational information as a vector value, or Euler vector value. So to do that, you need to use the function called crack transform. And what I need from here is a rotation. So C equal to 1. Yep. So the first one is 0, second one is 0. This is just the order, translate, rotation, and scale, XYZ. And the C is equal to 1. The pivot is 0, 0, 0. I don't think you need the rotate. So yeah, that's about it. Okay, so the output you want to get is the rotational angle for XYZ, and 0, 0, 1, set 0, 0, 0. This is the pivot for the translation, and finally you can input the matrix, and this will give you an angle value of this transform, light transform in Euler angle. Let's check. Okay, so this is in degrees, obviously. So X, Y, Z angle. And I want to convert this into a quaternion so that I can rotate specific vector value with it. So let's name this quat. And I'm going to convert this Euler angle into quaternion using Euler to quaternion function. Gonna convert it into rotation, and the order is 0. Meaning starting from X and Y and Z. Okay, now that and probably I need to convert this into radians, since this was degrees, but you need to use radians for this function. Okay, now that I have a quaternion, I can use qrotate to rotate the vector value using this quaternion. And the angle, the vector value that I want to rotate is this one. This is the default direction for a forward direction when the angle is equal to 0, 0, 0. So from 0, 0, 0 angle to this rotational angle, you can use this quaternion to rotate this original forward vector value and use the rotated one as a rotated forward direction. Let's see if that's true. So hopefully I'm getting a light direction out of this calculation, and let's check. I'm going to, for example, set the normal for each point with this light direction and check whether this is correct or not. So if I visualize the normal, looks like this, and if I look at the angle of the light, looks correct, but let's make it sure. Okay, so what I want to change is by changing the angle of this light dynamically like this, like that. I need to have the normal aligned same as this light direction. So if it's forwarding this direction, then the normal direction of each point should also facing the same direction. Let's check, and looks correct. So I think this is good. Now that I got the light direction, next thing I need is the camera direction so that I can calculate the angle between the light view, the light direction, and the camera. Okay, so And for the camera angle, I mean camera directions, what you need to have is the angle, I mean the vector from the camera itself to each point. Okay, it's not static like light direction, but the angle, the direction changes based on which point you're looking at. So in those cases, you need to have the position of each point, which you can get by accessing at P, and you also need to know the camera position, which you don't have it right now, so let's get that. So for the position, you can also use OpTransform from the camera path. So let's do the similar things like I did for the light transform. So I'm going to use the OpTransform to access the camera, get the camera matrix. Now next things that I want here is not the rotation but just the position. So camera position is crack transform, crack transform. So 0, 0 is the same. This is the order for the translate, rotate, and scale. This is for the axis X, Y, and Z. The third one is whether you want to get the position, rotation, or scale. If it's 0, that's translation. If it's 1, it's rotation. The other stuff is all the same. So something like that. And you should be able to get the camera position like this. And by subtracting the point position by camera position, you should be able to get the direction from camera to each point. Let's zoom in a little bit. And let's also bring the light a little bit closer to the plane so that we can see it inside the camera. I mean, the position of the directional light, it doesn't really matter because you're just looking at the direction, but just to make it easy to prototype. That's all it is for the position of the directional light. Okay, now that I have it, let's check whether if I got the position correctly or not. Okay, let's check. Okay, so I got this camera position 5.221 something, and if I check the camera here, okay, so this X, Y, oh, okay, so X is this one, and yeah, looks correct. Yeah, so I'm getting the correct camera translation or camera position, so that's good. So I'm going to name this as camera direction. Maybe I can normalize it. Maybe I don't really need it because I just need to calculate the angle, but just in case. So now I have a light direction and the camera direction. It's time you can calculate the angle between those two. So let's do that. Okay, so in order to calculate the angle, if you just want the angle between 0 to pi, the easy equation you can use is using a cosine, arc cosine, and off dot between the normalized light direction, which already is, and the normalized camera direction, which already is normalized. So, which should give you the angle between two vectors. Let's check. gonna convert the radians to degrees so that it'll be easy to see. Okay, so the angle right now is something like these. And let me draw some sketch how it looks like. So right now what I did is taking one point, and there's a light view, light direction, and there's a camera direction. Okay, and what I have just calculated is this angle here. Okay, but the actual angle what I want is actually this one here, theta quote. So theta quote is 180 degrees minus theta that I have just calculated. So so that I can use it for a rainbow threshold. And if the angle, theta angle, is in between, what was it? 137.7 to 139.6, you're getting rainbow. Okay, which in this case red to violet. Yep. So let's have this coded in Houdini. Sure. So now that I have this angle, let's make this degrees, or maybe I can just subtract it by pi, which is same as a 180 degrees. Okay, and maybe convert it into degrees after all. Let's check. So now the angle looks something like these. Okay. Some of the angle is within the rainbow threshold, I guess. So now's the time we convert this angle to a color value. Okay. Now, first thing I'll do is to convert the angle to this wavelength. Okay. Then later I'm going to convert the wavelengths into a color, actual color value, which can be seen as RGB. So let's do that. So if it's 700, then you get 137.7 degrees. If it's 400, then you get 139.6. So let's just use a fit function to convert the angle, which is in between 137.7 to 139.6, and convert it into a wavelength between 700 to 400. Okay, let's check that. Okay, and since I am using a fit function, it is being clamped with minimum and maximum. Maybe I don't really want to clamp it. Instead of clamping, maybe I should use other kind of function. If you use if it's not gonna clamp, but if it goes over like these angle or smaller than this angle or larger than this angle, it will just expand the threshold and gives you more than this or less than this. Okay, like that. I think this is much better. It's also giving you negative, which might not be a correct value, but that's fine because you're not gonna see those light colors anyway. Okay, now that I got this wavelengths, it's time we convert this wavelengths into a RGB using some kind of conversion algorithm. And I'm just gonna use the one that I found on Stack Overflow by searching convert light frequency to RGB. I don't know how much this is correct, but it says it's taken from science engineering spectra. So I'm not gonna say this is correct. I'm just gonna use it as a prototyping easy procedural algorithm. If you want to really have a precise conversion algorithm, then you should look at a link like these explaining all those behind scene algorithm. But I'm not gonna go in deep into this one today because I just want to visualize it. So I'm just going to copy and paste this one to use to convert the wavelengths to a RGB. See if this can be used. So I'm gonna paste it. Probably I need to rename some of it because this is being written for probably C or something. Okay, obviously I get the error, so let's fix this. First thing first, I don't need to use static, and probably I can just export vector value, and you cannot use double in vex, so you just convert it into float, and I'm gonna also convert this into a float constant value. Float double RGB float RGB. Okay, and the error is here. Okay, so here I think I need to create the vector value starting with 0. Okay. And okay, I can delete this math. Since this is creating as an integer value, probably the range is in between 0 to 255. Yeah. Where does this intensity mount? Yeah. So maybe I don't really need to have this one. I can just say 1, and I don't really need to make it as an integer value. And I don't need to make it rounded. Alright, then RGB.x, RGB.y, RGB.z. Okay, probably need to bring this inside a function. All right. I have a question. This rainbow physically correct? Well, mostly should be close to the physical simulations, but I am assuming that the water droplet is really small and sphere. But if you look at the paper that I showed, this shows more precise physical simulations, which determines the water droplet shaped more like this one, like a slimy shape, which is being affected by the gravity or something. And based on the size, the shape changes, so the refraction rate also changes, so the range of the rainbow also changes based on the water droplet size. So if you want to make it really physically correct, then you should follow something like these as well. What I'm showing here today is more of a simplified version, estimating that you are just using a really clean sphere water droplet. Okay, so you gotta make sure to understand that. Okay. Hopefully. Okay, so I have just brought up these wavelengths to RGB. Let's see if this thing works. So now I have wavelengths here. Let's use this function to convert it into a vector value, which should be a RGB value. Okay, and what I'm gonna do is to apply a color, point color with this value that I've just created. Let's see the result. And yup, I kind of already seeing some rainbow-like color here already. Looks good. And outside the wavelengths, outside these ranges, you are already seeing those colors as black, so that also sounds good. Okay, let's check how it looks like in terms of RGB. Okay, and you can see that by changing the camera direction, the shape of the rainbow changes, because the simulations is done between the camera view and the live view. So if you change the camera direction, obviously the shape of the rainbow changes. Interestingly enough. Okay, makes sense. And if you change the angle of the light, it also changes. The rainbow position. Okay. Okay, so hopefully this is correct. Not sure. But let me make it smooth shaded and have this a little bit more resolutions here. And I can use this view to close up, and looks like it is shown as rainbow color, so probably this is correct. Seems like you have tons of red colors here, but maybe. Okay. I have a question. I may be jumping the gun here, but can it be made smoother transition with camera change? Well, yeah, if you just change the camera view using those timeline, then you can make it smooth. But when you're just using the interface to change the camera, then you always get the result where the camera ended up. So I mean, if you seeing some expression here to rotate the camera, then you can smoothly change the camera. But if you want to do it like that. Okay, so let's say this is good, but let me also test out with the algorithm, the color changing algorithm that I found out previously. Looks like this one. And actually I have asked the chat GPT to create this function for me to convert the wavelengths to RGB. So let's see how different it is comparing to the one that I have here. Okay, so I am going to paste another function here. Let's make a note. So I don't know where the source is for this one, so I can't really say this is correct, but let's see. And this is what I got, and it's pretty similar to what I was having previously, so not bad. ChatGPT, but I'll go with this one, I guess. A bit brighter for this one. Okay, so far so good. Question: can you make these calculations on detail parameter? Sure. For single point, yes. I mean, as a single value, you can use that. You can do that. But the calculation, the angle calculation is done per points. So I think it makes more sense to do in point wrangle, but obviously, I mean, you could definitely do that on detail parameter as well. For sure. You just need to change this to detail, and instead of getting the point position from at P, just change it to something else. Static value. And that's all you need to do. Okay, so far the rainbow simulation seems good, and let's try this with point light as well. See how this makes difference. In terms of the point light, the direction is not single direction anymore, but more similar to camera. Meaning you are getting the direction from the point position to the light position to the point position, just like we did with the camera. So that will obviously change how the angle be calculated, and as a result you get different kind of rainbow look. So let's see how it looks like on flat plane. So I'm gonna create another light. And actually I don't really want to enable the light itself, so that I can just see the default light to see it effectively. I just want to use it as the guide geometry. So obviously it doesn't really need to be a light object at all. It could be a null object as well, but in case you want to use it as a light later. Okay, so this is the point light that I would like to use. Where did the rainbow go? Okay. And maybe I still need to enable to change the type, so I'm just going to set the intensity to 0 for now. Okay. Now for the point light, you just need to get the point position to get the light direction from the point position to each point. That's how point light works. So just like you did for the camera, let's try to do that. And maybe I want to have an option to switch between the directional light and the point light. So let's create a toggle so that we can switch between the directional light and the point light. Maybe instead of toggle, I'm going to use a ordered menu. And the first one is directional light. Second one is point light. Later, maybe you could use like spotlight, which is similar to point light, but the bright area is being limited with the cone, so might give you more interesting effect by limiting the area. Okay, so having those two, so that we can choose between point light and directional light, let's have another parameter to set the path for the point light. Using operator path, I'm going to give a path parameter for the point light. Try to delete that. Okay, and using the switch or ordered menu value, I would like to switch the light direction between the direction light and the point light. So where should we do that? So we have this directional light here, so let's first of all get the ordered menu value. Light type is equal to CHI. What's the name? Light type. Okay, and if light type is equal to 0, which is directional light, you get in these. And let's initialize the light direction as 0. Outside conditions, and fill in the variable inside the condition. Else, if light type is equal to 1, which means point light, then you want to do something similar to what we were doing for the camera. So I'm gonna copy this one and get the transformation from the point light path. Get the light position from the right transformation. Then calculate the light direction just like you did for the camera. The light direction is equal to normalized at P minus light position. This is it. Okay, easy as that. Oop. Reference to undefined variable light type, spell mistake. Okay, and if everything else is stay the same, think. Okay, so accept, and let's try to change it from directional light to point light, and you see something wicked here. So let's try to change the position of the point light to see how this affects the visual of rainbow shape. Interesting. So it is the relation between the camera and the point light direction. And based on the position of the point light and the camera view, you're getting something really interesting effect here on a flat plane. Alright, pretty interesting. And if you change the camera view, looks like these. Interesting. Okay, so that's that. That's that for the flat plane. Now, what I wanna do now that it's logically we can see that it's possible. We want to bring this into a volume so that it will look more three-dimensional, or make it more real. Make it look like a real rainbow, because in real physical environment the rainbow shows up in the water droplet or in the mist or something like that after the rain or something, where you have tons of small water droplets exist. So we want to create those kind of situations, and we could simulate that kind of situations using something like pyro together with the volume structures. So let's try to do that. So for 2D, let's say this is okay. Pretty simple. You just need one single point wrangle. Now's the time to do the simulations for volume, and I'm just gonna use a simple pyro volumetric simulations and use that result to view the rainbow. So I don't go deep into the pyro itself. I'm just gonna use the default setup by searching for a pyro. Let's use this pyro configure billowy smoke. Okay. I'm gonna change this a little bit because the default setup gives you a bit too much volume for testing. So see how it looks like right now. And it's pretty heavy for my PC here, because my PC doesn't have a good GPU. Let's see how it looks like. Okay, I guess I should have a light here. Maybe after all, makes sense to have a light somewhere. Maybe a distance together with the point light, maybe. Doesn't really make much effect. Well, let's just make it one, or maybe I just need the directional light to test out. Okay. Now the pyro, it looks like these, which is pretty, but there's too much volumes going on here for testing, so let's make it a bit lighter for a testing prototype. I mean, if you would like to have this kind of volume, then that's fine, but for me, no, it's not okay. So I'm gonna make it a bit smaller, or lighter. Okay, first of all, would like to start the volume from a square-like shape instead of torus. I mean, torus is fine, but just for my preference, I'm just gonna use a box instead. Okay, and I'm gonna make the size 4 by 4 and 0.1, so like something like really flat box. I'm gonna use these as a emitter for the pyro. Okay, connect this instead of torus. I mean, this is not really necessary. This is just for the light setup, so it's up to you how you want to make it. Now, these things are, I guess, fine. Attribute velocity, it's also fine, but one thing I want to add here is the color attribute to this one. Right now, if you look at it, you have where did I? Maybe, yeah, maybe I can add it additional attribute here and on pyro source. Right now I have two attributes. One is density and one is temperature. But I want to add additional one so that I can use as a color value. Okay, for later visualization. So I'm gonna add one custom one. Let's call this call and make a vector value. And as initial value, let's make it as a white value, 111 for RGB. Okay. Next, think I need to change some stuff here to make it a bit more lighter. Maybe not here, but the solver itself. First of all, go to the fields and dissipation. This is like a lifetime of the particles or the smoke. I'm gonna make it 1 so that the particle dies quicker, so that you have more like a fire-like smoke effect. Let's check. So you can see that the smoke is disappearing sooner. Now I don't really want to have these direction going this way, so let's also remove that. That is probably coming from here. No, that's not. Going upward is fine. Maybe going to the solver, and there is forces like wind somewhere. Sourcing. Nope. What was it? Let me check. I don't really do DOPS much myself, so I don't really know much about it. Okay. Let me see. So setup bounds, collision, sourcing, fields. That looks fine. Okay, here. So I don't really need wind. And for the other stuff, I think it's fine to have buoyancy or disturbance or turbulence. So Let's see how it looks now. Okay, now it's not really shifting, it's just going upward. Looks good. Yeah. So let's say this is okay. What I would like to do now is to visualize the map or calculate or simulate the rainbow on top of these volume. Now, compared to the flat plane, this has a depth, so the way the rainbow looks might be different than how it looked on plane. So we gotta have to check whether how does this depth difference will make visual difference. Okay. Now let's also check if I'm getting the color volume as an output. Nope. Okay, I'm messing here. So I think I needed to actually, maybe I don't really need it to add additional attribute here. Maybe I'm just gonna delete it and instead going to the solver, going to the field, there's a color option here, so maybe this will just create the color volume. There you go. Yeah, that's better. Okay, so I'm going to play a little bit so that I can have some volume, and from there I'm going to try to do the similar rainbow simulations that I did for 2D. This time try to do it for 3D volume. Okay, now before connecting this into a billowy smoke, looks like this. Now billowy smokes uses like something like temperatures and stuff to convert the color value, so I don't really need this, but instead I'm just gonna try to visualize. I mean, you could still use this, but just to make it simple, I'm gonna use my own rainbow visualize volume wrangle. Okay, so I'm gonna use the volume wrangle, and before that maybe I could cache the simulations, and let me open up the cache manager. Maybe I can increase the dopnet a little bit. And let me play this into the end for now. To cache it. Okay, wait for it. All right. Okay, so the simulations looks like these. Now obviously the opacity is a bit too low here, so let's make this more transparent or translucent, so that we can see through the smoke to make it look more like a low density mist. Okay, so how much RAM do you have? The Mac that I'm using right now, it has 64 gigabyte RAM, I think. Okay, so where was I? Okay, so the volume wrangle. So now I could bring all those calculations that I did here to a volume wrangle and see what happens. So I'm gonna just copy all these, paste it here. Might need to change something, and I'm already seeing something here. Okay, now I am going to add parameters. Maybe I can just press here, change these to different type. For this one, operator path. This one as well, operator path. This one as well, operator path. And for the light type, make it, I mean, for this one, I'm okay with the integer. That is because I'm just gonna copy these parameters from here, from 2D to 3D for ease. Okay, copy, paste. And finally the light type to here. There you go. Now let's change this to directional light for initial testing. Now I am already seeing something here on a volume. If you look from this perspective view, which is not related to the camera, seeing something like this. Now the resolution is a bit too low, so let's increase the resolutions a little bit, shall we? How much should I increase it? Going back to the pyro, I don't know, previously I think I was doing with this setup which was supposed to be fine, but looks like the resolution is a bit too low here. Where can I increase the resolutions? So this is 57, which is a bit too low. But anyway, I mean, for testing, I guess it's fine. Or not, I don't know. I mean, at least I could briefly see the effect here. And if I change the camera, yeah, it is obviously changing it. So, I guess that's fine for initial testing. Now, I don't really want to make the other color to be black, but I want to preserve the original color like these. A bit more, maybe a bit more low density, but preserve the color itself. So let's try to modify these color implementation or color applyment to preserve the original color but use the rainbow color at the same time. So to do that, let's see. First of all, I probably need to know what's the difference between the colored rainbow part and the other black part. And before going to those steps, maybe I might want to have more resolutions. This might give you a higher resolution. Let's see. Yeah, a little bit better. Okay, let's go with these. Okay, so first I'm going to determine how I can get the difference between the rainbowed part and the black part. The black part obviously has the low HSV value, so we could probably convert the RGB to HSV, hue, saturations, and value, and get the lightness or contrast value to check whether it's within the rainbowed part or not. So I have this color here. I want to check if this is really dark or not. So I'm gonna calculate the HSV using RGB to HSV. The last value is more like a contrast value. So if its contrast value is really low, then it means it is close to black. So so based on this value, I would like to change the volume color by lerping from original white color of the volume to the color of the rainbow using HSV.Z, which is the brightness. Okay, and let's see how it has. Now, looks more like it. Okay, now I think I need more low density for the whole volume. So for that, I'm just going to multiply the density itself by small number. And you have something like that. Looks better. A bit too light, maybe. Maybe I can make it as a parameter. I want to make the white part really translucent, but at the same time I want to make the rainbow part to be brighter. So in those cases, you might need additional parameters for the rainbow color by multiplying something like brightness here. Something like that, which should be more than one. So let's say maximum is 100. See what happens. Okay, something like that. Maybe 10 is good. Not sure. And maybe that's too light. Well, you choose the balance. Now if I play it, I see something like that. So for the directional light, maybe this is too light. For directional light, you always get the similar result for the rainbow, just like you did on the flat plane. The result you get is always an arc shape. Interesting. Even if you have a depth like these. But if you look from at this view, you can see that let's pause this a little bit. So from the camera view, it's always an arc shape, but if you look from the other view, other direction, looks like this. This is the actual camera view, but you are just seeing it like that on 3 dimension. So that's another way to look at the rainbow, and an interesting way to look at the rainbow shape. Oh, that's cool. Let's try the point light then. If I change this to point light, what would happen? Now, am I seeing it? It's a bit hard to see what's going on here. If I increase the... Okay, let's try to change the point light position or increase the brightness. That's too bright. Okay, where is the point light? So if I change the point light position, you're seeing something like oil on the water or something effect. Probably the rainbow you see on the oil is using the similar algorithm or procedures by looking at it, by looking at this one. Now this is a bit too bright, I guess, but what I wanted to show is these interesting stripe pattern on 3 dimension. Previously, if you're on 2D, you are just seeing one strip, but becoming 3 dimension, you are seeing multiple strips because of the depths. So that's what's interesting about this point light based rainbow. Okay, let's see. It's really hard to find the best position of this point light to clearly see. Now this, it also shows the changes of the point light, I mean the rainbow and stripe. Okay, well, this is up to you to test. I mean, obviously the resolution is not that good right now because I'm choosing kind of a low res value to test. And maybe the brightness is a bit too much as well. So but I guess you could feel the interestingness of this one. How about making this wow. What if I resample the volume to make a bit more high res? Would it change filter scale? Okay, this doesn't really change. Oh wait, not this one, but this one. Okay, now the number of volumes changed. Okay, this didn't really change much. Maybe it's the viewpoint what's important. Oh well. At least I think I was able to show what I wanted to show here. I have a comment that looks like a bit like a projection trapped through a dust. I think that's exactly what this is. This is interesting. Let's play this out. So if it's just a directional light, it is just a normal arc-like shape, but by using light type, light point light, you could create some interesting visual effect. It's pretty interesting. Yeah. And probably by changing the perspective of focal length of the camera, that might also change the effect. Let me try that as well. Right now the camera's focal length is equal to 1. Huh. 1, that's interesting. Let me change this to 30. And aperture to, I don't know, 45 or something. Yeah, this also affects the angle, so maybe not, because I'm just using the point position of the camera, so maybe it's not really important. But anyway, that's how I did it, and let me look back at the things that I did previously, see what's different. Well, this one looks more subtle. I mean, looks more the resolution looks better somehow. So maybe I'm missing something here. Not sure what that is. Let me try to change that. First thing I could try is trying out the ChatGPT's way to change the wavelength. See if it's gonna change something. A little bit, a bit cooler color. Well, other than that, what else? Let me check the pyro setup that I did previously and try to use the same setup. Okay, so starting from here, same value, bounds. I think I didn't really change anything here. Nope. Collision, nope. Source. Source is the same. think. Temperature, velocity, yep. Feels. So I say I have dissipation equal to 1. Cooling rate, yeah. Same. Shape. Buoyancy, disturbance, turbulence, all the same. Look, density scale. Maybe this one is a bit different. Nope, it's the same. Interesting. Why am I getting the different result? So previously it looks like this, and by using the volume wrangle it changed to this, so maybe something inside a volume wrangle is different. Let me check. So I have these density multiplication, which is same, multiplying by 0.01. Okay. The brightness, where does this brightness comes from? Where is it? Okay, so well, it's just using the fixed value like 20, so pretty similar. So if I change this to 20, looks like this. Other than that, it's all the same, I think. So nothing different. Maybe this is the right view. Just the matter of the right angle and right point light position. Maybe that's it. Or actually I am having we're disabling the directional light, but instead I was using the point light. That might be the reason. Okay, now this looks a bit better. I have so many stripes here, but that is due to the position of the point light. So if I make it closer, I should have small number of stripes like that. It's very interesting. Yup. Looking good. Looking good. Yeah. So that looks good. This is more like it. All right. So that's it. That's it for simulating the rainbow on volume, both on volume and 2D plane. Since I did it for volume, I mean, you could also use the same method to apply it on like mesh surface or anywhere. So try that on your own. Okay, so that's it for today, I guess. Let me know if you have any questions or feedback or suggestions. If not, I'm gonna end the live for today. and prepare for the next one. Yep. Well, thank you for watching. I mean, I am going to, as always, I'm going to upload the file and paste the link to the video description page of this live stream. So come back later to download, test it out by yourself. Yeah, the next week's topic is to create the 3D bubble simulation without using physics, which is kind of related to the last live stream that I did, which was weighted centroidal Voronoi tessellations. I'm gonna use the same algorithm to create the bubble motion on 3D volume, and as an additional bubble making simulations, I'm going to create the curved inner wall for the bubble to make it look like more like a bubble in real world. I'm not sure how it looks in real world actually as a cell, but at least I was satisfied with the results, so maybe you might be also interested. You might also like it. At least it looked pretty on rendering, if that's all matters. Okay. Tom Prism. Sorry, I don't know about that. Let me search for that later. Okay, so that's it. Thank you for watching. Thank you for coming this late night, at least in Japan. Hopefully I'll see you next week on the same time. Okay, good night, and